Welcome. This is a model of the Flying Scotsman, the first steam locomotive to reach 100 miles per hour, a huge achievement. Oh, isn't she beautiful? So for my first test, I want to look at what's the maximum angle, or grade as we call it in the train world, the Flying Scotsman can climb. So in real life, trains can typically go at a maximum grade of about 2 degrees, which means they can't just shoot straight up a mountain. Instead, they would have to curl around, ultimately reaching the top. So for our experiment, we're going to use a couple of things that are familiar to me from my childhood, namely these composition books and this. So this is a plastic riser that actually came with an old Thomas & Friends that I own. So the idea is that you can stack these up on top of each other and really go crazy with them, and then just have the rails over them and then have the train travel over them, creating an incline. So we'll be using that for our test. So let's head to the track and get started with our first test. So as you can see, it took us 7 composition books to finally get the Flying Scotsman to do what's called wheel slipping. So this tells us that the forces on the incline for the train are fully balanced. So yeah, I'll just give you a second to really enjoy that. Now for the calculations, we're going to get the help of a very special friend of mine.
Oh, cheerio. Hello, I'm Matt Sakindi. Let's get on with the first test, shall we? We're trying to find what is the maximum theta that the train can climb. So we experimentally determined that it took 7 books, okay? So we'll just start with the force diagram, and this is 65 millimeters. So you can probably imagine that it's time to use some trig functions, which you are correct. We're going to be using tangent in this case. And we find that theta is approximately 6.15 degrees. Earlier, normal Akindu mentioned that trains typically take a 2-degree grade, and there's a couple of reasons why we got an experimentally higher theta, because primarily we only looked at the train here, typically, or the engine rather. Typically, we would have a whole train behind the engine, so that would take a much longer, that would take a much smaller grade. Second, we also know that it's better in the real world to err on the safe side. So I think a cool 2 degrees would be fine. We don't want to push the limits here, especially when the trains are carrying passengers, for example. Namaste.
Hi, welcome back. So for my second test, I want to look at what's actually powering the train, what's actually causing it to move. I mean, you saw in my demonstration that when I turned this dial, I was able to increase the speed of the train, but what's actually happening there? So I have this voltmeter here because I feel like we're going to have to deal with some electricity, but there's just this one component here that I'm just not sure. I can't... A potentiometer is a variable resistor, meaning turning the dial increases the resistance, increasing the voltage. Hey, so what if we tried, looking at the maximum resistance across the potentiometer or something?
Slapping idea, lad, but it's actually potentiometer, not potentiometer. Let's get back to the track.
After hooking up the track to the voltmeter, I found a maximum voltage of 15.21 volts.
Sorry I'm late. This one's gonna be a monster. So what we want to do is find the maximum resistance of the potentiometer. So there's a lot here, but we're gonna break it down. So what I wanted to do was start with power. From mechanics, we learned that power is force times velocity. But then in electricity and magnetism, we learned it as, in one form, the potential difference squared over R. What I did here is just combining those two, setting them equal to each other, because it's really the same power that's going from electrical power to mechanical power. Because I end up getting the energy equation, actually, where it's power times time is equal to the final kinetic energy of the train. But the one thing that bothered me was, what can I do about the time? So I used the setup, as you saw previously, to manipulate the kinematic equation so that I could get time. Now we know everything here, as shown here, and then we can find that maximum resistance which we were looking for. So now let's get to it. And ladies and gentlemen, we have it. We've solved for approximately 110 kiloohms. this is a reasonable amount for a resistor. So any other amount of resistance based on the dial, we can calculate using just the fact that the dial is a circle. So say if the loop was only halfway, we would just divide this by 2 to get that resistance. So knowing this, maximum resistance is really powerful when it comes to a potentiometer. Back to you, Normal Kindu. Namaste.
Hardcore model train enthusiasts tend to be extremely good at electronics. Take this professor from MIT, James Roberge, who taught an upper-level electrical engineering course called Electronic Feedback Systems. He too was an avid model train fan, but as you can imagine, he takes things to a completely different level. At the end of this particular course, Roberge decided to implement ideas from both the feedback systems course along with principles that we covered together. When we looked at the incline, it was easy to see that the train slowed down when the Flying Scotsman reached the slow part of the track. Intuition also tells us that the train would speed up going down inclines. So, this man creates his own locomotive that sends an electronic signal indicating what speed the train is going, and then the voltage is finally adjusted, most likely using a small set of resistors, to adjust the speed as needed. The result, that being that the train now goes at a constant speed up and down the incline, may not appear to be a staggering visual, but the intricacies of the inner circuitry is nothing short of beautiful. Richard Feynman once noted how poets dismiss science as something that takes away from the beauty of things. He refutes this, saying, quote, "I too can see the stars on a desert night and feel them, but do I see less or more?" End quote. An understanding of the physics principles that bring together both model trains and real steam engines to life as its pistons heave on a trek up a snow-covered mountainside, or in the summertime as it gallantly runs past a station whistling, "Look at me, aren't I splendid?" does not tarnish these romantic images. Instead, the train's beauty is amplified in mitigating the sheer sense of disbelief one feels with every turn of its wheels. Thank you.
All in a day's work, eh, Paddington?